Hello students, good afternoon to you. So you are most welcome in the video lecture of LNT College studio. So my topic is actually ionization energy of alkali metals. So ionization energy, first we will define what is ionization energy, what are the factors that is responsible to understand the ionization energy, and hence, so since we are talking in case of alkali metals, so in the previous lectures we have studies about the metals of alkali metals like lithium, sodium, potassium, rubidium and cesium, and the atomic number of lithium, so that is 3, and for sodium 11, 19 for potassium, 37 for rubidium and 55 for cesium. So if you talk about the electronic configuration of the alkali metals, so then you know that, so the outermost electronic configuration is, suppose that this is your helium and this is your 3 so this is your actually 2s1, right? So this is your 2s1. Okay, so this is the electronic configuration of lithium, and it is just one electron extra than that of the helium. So electronic configuration of the outermost cell, that is 2s1. For sodium, so that is neon and it has 3s1, right? And for the potassium, this is argon and it has the outermost electronic configuration which look like 4s1. And for the rubidium, so that is the electronic configuration of the krypton, and the outermost configuration is 5s1, right? And for the cesium, so that is the electronic configuration of xenon, and outermost electronic configuration, so that is 6s1. The francium, in which case the outermost electronic configuration, so that is 7s1. So due to the radioactive nature, so we are not going to discuss here about the uh, francium. Okay, so what you are observing here is that, so there is always increase of cells, right? So because of the principal quantum number, so in this case, principal quantum number, that is n is equal to 2, n is equal to 3, and n is equal to 4, n is equal to 5, n is equal to 6, right? So as you are seeing here is that the principal quantum number increases from 2 to 6. Okay, so if we look on the principal quantum numbers, so then you can say that the number of cells actually increases as you move from lithium to cesium. So you know that every metal has a nucleus which is a positively charged in the centers, right? So suppose this is your positively charged nucleus, okay, of any alkali metals. So the principal quantum number do 2, it means it has two cells, like, so that is K cell and L cell, right? And the valence cell is, this is the valence cell. So valence cell, right? And in case of sodium, the cells are KLM, right? So KLM, but the valence cell is M. So this is the valence cell. and for potassium KLMN, right? So this is the valence shell. Each cell is composed with subcell, right? So cell has subcell, right? So subcell for the alkali metal is fixed, so that is S subcell, right? So S subcell contains one electron, right? One electron. And in case of lithium, this one electron is located in 2s orbital. So, and this is the closest to the nucleus. So, suppose 2s is located here, right? And this is your 1s, right? So, this is your 1s, this is your 2s, okay? So, and this is your 3s, this is your 4s, and suppose this is your 5s, and this is your 6s, right? So, what you are observing, since each s orbital contain one single electron, so in case of lithium, the electron is situated here. So, in case of next sodium, in case of potassium, in case of rubidium, in case of cesium. So, what you are observing here, the nuclear positive charge attract this negatively charged electron towards itself. So, because of the electrostatic nuclear force. So, the outermost valence electron, so that is located in the s orbital, is very close for the lithium. So, there is a less distance between positive charge and this outermost valence electron. So, the electrostatic nuclear force is very high in case of lithium, okay? So, as you move from lithium to sodium, so in case of sodium, again the distance between the positive charge and the outermost electron, that is 3s electron, is increases, okay? So, nuclear force is little lower in that case. As you move towards potassium, again this distance, right, this distance increases, right? So, increased distance lowers the nuclear force or electrostatic force between the positive charge and outermost valence electron. So, again we move towards rubidium and cesium. So, the distance continuously increases from the positive charge to the outermost 5s electron, and in case of cesium, this is the largest distance, right, from the positive charge to the outermost 6s electron. So, electron is bound with the nucleus, right? So strongly in case of lithium, right? So, outermost valence electron in case of lithium is strongly bound to the nucleus, but the outermost electron for the sodium, so experiences little lower nuclear force. So because of the increased distance from the positive charge to the outermost electron. But in case of potassium, there is a further increase of the distance from the positive charge to the outermost electron. So the force, so that is electrostatic force, is further reduced. So what you are observing here, as the distance from the positive charge to the outermost valence electron increases, the nuclear force decreases. So outermost electron will be loosely bound with the positive charge nucleus, right? So, so from the point of view of this electrostatic nuclear force, so the removal of electron from the outermost valence electron depends on the extent of degree of the nuclear force that is attracted to outermost valence electron. So in what way we can define the ionization energy? So ionization energy is actually measured in kilojoule per mole, right? So ionization energy means energy for ion, energy to create ion. So, so it may be for the positive charge to create on the metal. So suppose in case of lithium, right, solid state. So in the solid state lattice, in the metallic lattice, outermost electrons are actually so strongly bound with the nucleus, so it is not easy to remove the outermost electron. So, so before removal of the electrons, the lithium solid metals should be converted into isolated gaseous metal. So this is generally done by under the application of the heat. So solid state lithium is converted into gaseous state lithium. So the electrons now feels flexibility. It means electrons are mobile in the lithium in the gaseous state. So because of the soft metallic lattice, so electrons are actually mobile. So once this gaseous lithium, so under the application of heat energy, lithium undergo ionization in the gaseous state by removing its valence electron. So in this process, basically the energy required, IE, so that is ionization energy. So the energy required to remove its valence or outermost electron from the gaseous atoms is called ionization energy, right? So if one valence electron is removed from the outermost uh, valence shell, then it is called first ionization energy, and the first ionization energy is indicated by IE1, right? So for the lithium, this is the first ionization energy. Similarly, we can see for the sodium. So sodium in the solid state. So once this sodium is heated, so the phase change occurs, so that is Na in the gaseous state, right? So further, if it is heated or energy is supplied, so this sodium gaseous will be converted into sodium cation plus electron is removed. So this is IE1, right? First ionization energy. So similarly, other alkali metals can be uh, shown through the implication of the heat energy and its first ionization energy. So what is the beauty of the this cation? So this lithium plus cation, what is its structure? So its structure means here only two electrons. So two electrons is look like helium, right? So helium has a atomic number of 2. So it has electronic configuration 1s2. Okay. So this is the electronic configuration of lithium plus, and helium is the noble gas which has closed shell. So s orbital is completely filled, and once the s orbital is completely filled, the metallic lattice, ionic lattice is much more stable. So this lithium plus cation is highly stable because of the closed shell configuration, right? And so that is why they easily uh, remove its outermost valence electron. So in case of sodium, actually, so what is the configuration? So the configuration of the sodium cation gaseous is, this is neon. Okay. So in case of neon, what is actually electronic configuration? So that is 1s2, 2s2, and 2p6, right? So this is the electronic configuration of sodium plus gaseous state, that is 1s2, 2s2, 2p6. So from the electronic configuration, you can see here s orbitals and p orbitals, so they are completely filled and they are completely closed. So the filled or completely closed systems, so indicates that sodium cation is more stable, and the stability is similar to the neon, which is a noble gas, right? So in this case, ionization energy E1. So what you expect, because the valence electron in this 2s1, right? In this case 3s1. So the distance is little lower from the positive charge nucleus to the outermost 2s electron. So the energy which is required to remove this valence electron is actually will be very, very high. So that is a positive quantity, actually positive. So IE1 for this lithium is greater than sodium. So lithium and sodium, potassium, rubidium, and cesium, right? So this is the order of ionization energy. So ionization energy decreases in the group. Decreases in the group, right? So because of the increased distance between positive charge nucleus and outermost s orbital electron, that is valence electron. Okay. So this is the trend for the alkali metal in terms of ionization energy. So the ionization energy, so this is the only for first ionization energy. You can say IE1, IE1, right? So first ionization energy decreases. So what you think about the second ionization energy? So suppose for the second ionization energy, so that is lithium. So in case of lithium plus gaseous, right? So if you supply the amount of heat, right? So Li2 plus gaseous and further electron is removed, then the ionization energy is denoted as IE2, right? So the IE2 second ionization energy will be either low or high, so it can be understood through the electronic configuration. So in case of lithium 2 plus, the electronic configuration is 1s1, right? So it is similar to hydrogen, right? So this is the electronic configuration of hydrogen, and it has a electronic configuration 1s2, so that is the case of helium, right? So because of the stability of this orbital, right, the electron removal is very difficult because stability will be disturbed, right? So the energy will be required in a very high amount. So because uh, after removal of further one electron, so this will create one s1, which is similar to the electronic configuration of hydrogen, right? So this is small, so lithium plus is small than lithium, right? So increased positive charge on the nucleus will tightly bind to the closed shell electrons, right? It means the high positive charge density, so that will bind one s2 electron so strongly that the electrons cannot be removed easily. So if it is removed, then the large amount of energy required. So ionization energy of second ionization energy for the alkali metal cation is larger as comparison to first. So IE2 is greater than IE1, right? So if you think that the third ionization energy, then Li2 plus gaseous through the supplement of heat energy Li3 plus electron. So this is your 1s1, and there is 1s0, right? So there is no electron present in the system. So this is not stable in the nature. So this is not stable in the nature. So third ionization energy in case of lithium 2 plus, so it is not actually observed. If it is observed, then it will be very high. So for the third ionization energy, IE3 will be very large. So third ionization energy is very high compared to second ionization energy, and the first ionization energy is the low for the alkali metals. So we have collected the data for the first alkali metals, so that can be understood here. So in case of alkali metals, so the data look like for lithium, sodium, potassium, rubidium, and cesium. The first ionization energy IE1. So IE1, in case of lithium, that is 520.1. In case of sodium, that is 495.7, 418.6, 402.9, and 375.6. And the second ionization energy IE2 for the alkali metals, 7296 kilojoule per mole, 4563, 3069, 2650, 2420, 2420. So this is the ionization energy for alkali metals, right? So in case of lithium, so that is only 520 kilojoule per mole, and in case of cesium, it is 375.6 kilojoule per mole. So the ionization energy, that is first ionization energy, decreases in this alkali metal group first. What is the second ionization energy? So there is 7,296 kilojoule per mole. So actually that is much more high. So the electron is, since electron is removed from the noble gas configuration, so the second ionization energy is very high. And the second ionization energy also decreases in this group. So here 7,296 kilojoule per mole. But in case of cesium, the second ionization energy, so that is 2,420 kilojoule per mole. So in this way, you can say that second ionization energy IE2 is greater than IE1, right, for the alkali metals. And the ionization energy depends on the electronic configuration and type of the orbital involved. So S, P, D, F. So the electron can be removed from the any of the orbitals. So since alkali metals are S block elements, so the energy actually for the S subshell is removed. Okay. So for the alkali metals, actually because of the larger size in the periodic table, so all alkali metals actually possess lowest ionization energy. All alkali metal possess lowest ionization energy, lowest ionization energy in the periodic table. So ionization energy, what factors actually depends? So if there is a alkali metal cation M, right? So this is the alkali metal M. So ionization energy depends on the charge on the metal, right? So it depends on the charge, directly proportional to charge on the metal, right? So greater the charge density on the metal, so harder will be the uh, to remove the outermost valence electron, and hence more ionization energy will be for the highly charged species, right? Size. Ionization energy size. So smaller size alkali metal or any other element, so which possess more lattice or more ionization energy, and bigger size alkali metals requires large small ionization energy. So small size metal possess high ionization energy, right? And large sized metal possess small ionization energy accordingly. So charge and size, these are the two factors. So will be actually uh, in the consideration of the ionization energy. So S orbital for the alkali metals are the valence shell, and which can remove its electron through the supplement of the heat energy and accordingly ionization energy, right? And if the noble gas configuration of the metal, so then it has very high ionization energy. So if the electronic configuration look like noble gas configuration, then the ionization energy will be very high. So because of the stability factor, so because of the closed configuration, because of the complete filled shells or orbitals, the stability is maximum and nuclear force on the valence electron is very high. So ionization energy will be very high for the noble gas configurations. Okay, so this is the um, actually idea about the ionization energy, and the ionization energy is a always positive quantity. So it will depends on the uh, charge and size of the metals. Okay, thank you students for listening these topics, which will be helpful to understand the chemistry of alkali metals for the semester of a undergraduate students. So next video, so again I will meet with you. Okay, so bye. आइए